Okay, I think we're about at the top of the hour here. Thank you all for joining us. We'll be discussing, are you data ready for predictive maintenance in energy today? My name is Gabe Prado. I'm a product marketing manager for Spark Cognition, working with our predictive maintenance solution. I actually have a background in data as well from National Instruments. I worked on a product management team for data acquisition. Now, I want to introduce our main speaker today, Dastan. He's one of the data scientists on our technical sales team. And his role is really interesting because he sits right in the middle of the data and the business problem and helps to marry those two things together. So he's highly involved with our customers, working with their data to solve their problems, and has a real good wealth of information to share today. He also has a background in entrepreneurship and engineering as well. Now, the format of our webinar today will be somewhat like a podcast. We'll be kind of chatting today. We'll be monitoring questions as they come in, and spend some time at the end specifically around Q&A. And we will make this video recording available to all the attendees and all those who weren't able to make it today. So without further ado, we'll go get right into the agenda. Today, I'll spend a minute just kind of level setting on what Spark Cognition, who Spark Cognition is, what we do. We'll spend a little bit of time on the why machine learning for predictive analytics. Spend most of the time on data itself, data quality, quantity, accessibility, and reproducibility, and then walk through a case study where this all comes together. Now, at a real high level, Spark Cognition is an AI company and leading AI solutions company based out of Austin, Texas. We specialize in machine learning and natural language processing, and we apply those technologies to different problems in industry. Now, we've been around for about 5.5 years, and we're expanding across the globe. So we have presence in Dubai, we have folks in Japan, Mexico, and Europe. So it truly is a multinational presence. Now, with our funding that we've captured, we're using that to invest in both the science and the research in AI, as well as the commercialization of this technology to solve some of our customers' biggest problems. Now, specifically in the industry space, what I'm really excited about is, we're solving problems that touch millions and millions of people. Specifically in power gen, our customers are generating power that their customers touch every single day, every time they turn on a light switch. So it's exciting to be part of that piece that is helping to advance some of the most important interests of our society. So I'm going to hand it over to Dastan real quick, and let him take it from here.
Hello, everyone. Very excited to be here, by the way. And I guess you're looking at a slide where it's basically talking about why machine learning for predictive maintenance. So the traditional approaches, they are great. They're effective for a majority of cases. However, where machine learning really comes in and shines is for those unknown unknowns, right? Whenever you're trying to discover, with traditional methods, you're working with tolerances across sensors. Here, with machine learning, you're able to integrate multiple sensors and discover operating modes, various operating modes, which might be indicative of potential failure or null behavior. And we're going to get into all of that later on. So, and obviously, one of the main advantages of also deploying predictive maintenance solutions, that are AI-based is the fact that we do have a retiring workforce that are subject matter experts, and I just wanted to stress that it's important to capture that knowledge in AI models that can basically sustain and transfer that knowledge onto the new, new subject matter experts, or the ones that will start developing skills, not only hopefully with the generators and the utilities space, but also with artificial intelligence. So. All right.
Yes, I think one way of framing this is, we're moving from a human-defined approach. Now that we can process the data more effectively, we're moving to a data-defined approach, which is letting us explore this data and apply it in new and interesting ways. So
that is right. That is correct. So Over here, I guess every single AI project, at least, it has certain components, right? We've broken it down to these 6 components here, where the critical part is actually defining the objective. So in the end, although I do love to play around with data and numbers, in the end, it is all about solving a business problem. So so defining objectives is the most important thing. And then also you have to assess the data. You have to understand, what that data means. You get to work with subject matter experts. And then AI is still software. So you have to feed the model with data that's been pre-processed and that looks, has a certain structure to it. So that's very important. And then on to deployment, obviously, and selecting the model, training the model onto deployment, and then obviously from there on you might go, iterate on another cycle to discover a new pattern or a new use case.
Yeah, so it's a good topic to discuss. I know when I'm talking with customers at trade shows or whatnot, a lot of customers are trying to grasp, okay, what do we need to know about our data? So I know with working with customers, we've kind of distilled this into 4 key dimensions around data that we're going to discuss and spend most of the time on in this podcast today. Now, I think the first and the kind of biggest question is, you've kind of heard the phrase garbage in, garbage out, right? But I can't think of a more relevant use case for that than machine learning,
That's right?
Can you spend a little bit of time just helping us understand, more about data quality? So maybe starting with okay, what does a bad data set look like?
Yeah. So a lot of times there are a couple of approaches to predictive maintenance. The ones that we use is more of on unsupervised learning. So the other one is supervised learning. So typically with supervised learning, with all approaches, you need as much data as possible. And a lot of times, why we need a lot of data is really all about making sure that you capture the asset's kind of behavior over a long period of time. So you're capturing various operating modes, how the assets behave in various seasons under various workloads. So all those things are important, and that's part of the reason why we need to train the model to have that information. So basically, to get into some more details here, so a good quality data set versus a bad quality data set. So some of the details is missing data. So a lot of times, for example, if your sensors are sampling at different time, at different frequencies, you need to have ways to basically kind of how to stitch it all together into a common kind of a time series framework, right? Some sensors will also they go bad or they drift or there's various issues. So you also need to account for how important that sensor is, right? For your model. If it's an important sensor, you have to work with the client in trying to figure out how would you handle something like that, right? So outdated. So unlabeled tags. I feel like that's obviously for somebody who is a subject matter expert who's looking at this data day in and day out, that information is familiar to them. For somebody like us who's coming in, it's best for us to actually understand what a specific tag means, what it does. So it's very important to understand whatever that asset that you're working on, you have to understand how it works and what kind of information what kind of information do we need to extract out of all those sensors, right? All the data that those sensors are spitting out. So, Gabe, do you have anything to add here, or?
Yeah, no, I think you're kind of right on track where, part of this is mechanical, right? It has to deal with, are the sensors applied properly, right? Are we getting the right readings? And then part of that is still dependent on the human itself, right? So we have to look at both of those factors. We're actually dealing with that data quality. Are there the controls in place to make sure that the data is clean enough to be able to be used? Because like I said, garbage in, garbage out, right?
Right.
You can't build a good machine learning model without having data that you're confident in.
Yep.
Now, the data is still not going to be perfect, But can you give us a little bit of insight around like how Spark Cognition deals with bad data, how machine learning and Spark Cognition deals with bad data, for instance?
Yes. So, I mean, effectively, you hope to capture before you actually deploy the model, you have to train the model. And so during the training phase, our data scientists are the ones that are basically working with the customer, with their team. Again, as I said, just trying to figure out what kind of things, what kind of curveballs could potentially happen when the model is deployed. So ideally, in a production environment, you want to address as many of those issues as you can. So how do we deal with that? We actually do have multiple tools that we deploy for that kind of purpose. For example, part of our ETL tool is called Hermes. So Hermes is basically an engine that sits in front of the model that will be deployed, and it basically pre-processes the data and transforms that to be fed into a model that hopefully by this time that you already have trained. So does that sort of answer your question?
It does. Is there a data scientist involved at all in that process? Like, what's the governance?
Yeah. So typically, the data scientist is usually involved during the training of the model, and prior to the training of the model, and obviously during the training of the model. So a lot of times there's a process called validation of the model. So you have to not only prepare and curate the data, but once that data is prepared and curated, you have to train a model on the subsample that you receive from the customer. So, and that's part of the reason why we call that, there's a holdout set that you want to make sure that the model hasn't seen. Otherwise, there's a concept called, data leakage. So during, you want to make sure that your test set or the holdout set does capture, generally speaking, what the model is trained for, but at the same time, it's not something that the model has seen.
Sure.
So, does this make sense, Gabe?
It does. It does. Now, I definitely want to make this, practical for our customers. So maybe you can share a customer story, but if we can make some recommendations for how can a customer actually go in and start to fix some of these fundamental problems with their data? How can they actually go in and start to fix either the hardware issue, the human issue? Like how can they start to improve their quality of data?
Yes. So, I mean, typically, a lot of times sometimes there's only limited things that customer can do prior to an engagement. A lot of times we're dealing with customers that may not have the data science expertise. They may have all the subject matter expertise they need, but a lot of times what may happen is that they just may not understand that, okay, we didn't know that, sampling rates are a big deal here, right? So I mean, things that a customer can do to make our lives easier, obviously, is going to be effectively, hey, can we make the data more or less look like a table, right? Where you have your features going across your columns, you have your time series data, for example, going across your rows, right? And then making sure that if there are any kind of gaps or information where sensors are not spitting out the data that you need, sometimes there's just no data, right? Yeah. So addressing questions like that would be pretty important. Otherwise, I mean, we have techniques how we can basically fill in those gaps, but a lot of times it's best to kind of have a good insight as far as what is the best method to, how to impute the missing data or bad data.
Sure. So if I distill that, what I'm kind of taking away here is that there's an initiative around data governance, right? Then you have to have the systems in place and the documentation to make sure that you understand what all this data means in context. The more standardized, the better. And I know for some of those, we can work with vendors such as like OSI Soft.
Oh, that's right. Yeah.
Can you tell a little bit more about?
Yes. So we partner with a lot of these vendors that like OSI Pi. OSI Pi is probably, I can't say that they're a monopoly, but at the same time, every single time we work with any kind of industrial assets, we actually notice that OSI Pi is the chosen kind of historian, if you will, for time series data. So there's obviously when the data is there, we kind of have certain techniques that we apply. A lot of times, for example, a sensor might be capturing acceleration data, and it might be capturing multiple frequencies. So you have to do what we call fast Fourier transforms to basically figure out what are those amplitudes across various frequencies, right? And that's what gets ingested into the model. So anyway, there's probably more, it's a little more detail than you probably want to hear, but am I kind of answering your question?
Yeah. Do you have a customer story at all of someone that you've worked with closely that has kind of gone through some of these data quality issues and how we worked together to
Yeah. I can't off the top of my head. I guess I don't feel comfortable mentioning customer names specifically, but I'll just mention an industry.
Yep.
So a lot of times what happens is that you may have an oil and gas company that has a third party that that they basically outsource their data management or data collection to a third-party vendor. And then we typically would effectively work with that third-party vendor. And so we, like for example, there's lots of vendors like that, right? So in this specific instance, I'm thinking of a company called Cognition. They're not related to any specific one, but at the same time, they have a great infrastructure. You're able to basically log into and access data. I mean, obviously, it's the IT security policies, but once you actually have the data, there's plenty of information there. Sometimes you work with a vendor that, like for example, with our defense side, the government, a lot of government, I guess like agencies / defense entities, what they do is they specifically order their equipment to be manufactured by various providers to specs that would be exclusively used for that use. They're not to be shared with anybody. So a lot of times we're working with a lot of these vendors where it's just a discovery process, right? You have to have that subject matter expertise.
Sure.
In place.
Sure. So I know, kind of moving on here, I know another closely related topic to quality is actually the quantity of data. Now, we mentioned that a little bit earlier on, but let's do a little bit more of a deeper dive on how much quantity do we actually need for a model to be successful?
Yeah. So again, I sort of alluded to it earlier. It all depends on what you're trying to do, right? So really the idea is you're trying to capture the various operating modes that are in there, right? So in some instances, for example, if your control environment is not subject to seasonality and weather patterns and whatnot, you might get away with only a couple of months of data, right? You don't really need to capture ambient temperature or something like that, right? In other cases, you might be dealing with a refinery that's important. Ambient temperatures are it's a key part of how much energy goes into it. There are different modes that a whole refinery or a certain piece of a refinery experiences depending on what those conditions, environmental conditions are. And so it really kind of depends. But generally speaking, the thing that we're going after is we're trying to capture a full cycle of various operating modes for whatever equipment that we're trying to apply predictive maintenance to.
Sure. I know specifically for like the energy and utilities space, we've done a lot of work with like combustion turbines and compressors and generators, those type of assets. So I agree with you. The more history of asset failure, the better. But there's also situations where we don't have all that labeled history. So kind of backing up a little bit, obviously we want as much data as possible, but is it possible to have too much data? And how do we handle big data these days, right? How do we actually make everything usable enough so that the machine's not biased one way or another?
Yeah. So it's that approach, generally speaking, let's say you can have a lot of data. If you think of it in terms of a table, right? You can have a lot of data going across. Let's say you have too many sensors, and then you have also a lot of data, just a lot of history, right? So generally speaking, having history is actually a good thing. You do want as much history as possible. So you want your data set to be quite vertical. Now when it comes to data that basically is wide, it has has a lot of columns, a lot of features, you may discover that that certain sensors are highly correlated with one another. So you don't need to capture every single one of them. There's tons of techniques that we use. We use principal component analysis. There's a kind of a neural networks version of that using autoencoders, where we're able to capture those latent relationships between sensors. But basically, it's a one variant or another of basically principal component analysis, where you basically squash multiple sensors, and you try to find out the greatest variance, if you will, right? And then you find your initial components, and then you go to the second one, with the greatest variance across rows. And so that way you can basically reduce a data set that may be coming in, 500 tags. You're able to kind of drop it down to, let's say, hey, if we just track these 10 tags, well, not 10 tags, if we capture these 10 principal components, that captures 99.9% of all the variance that's there in the data. So does that make sense?
It does. Now, I think the next leading question here is like, all right, so we've kind of relied on a machine learning algorithm to reduce these to the right components, but how do we validate it? How do we make sure that we found that right balance? Can you deep dive on that a little bit?
Yeah, so again, it's a lot of times, it depends on the use case. We sometimes try to target various, so for example, you have your accuracy, you have precision and recall, various things that you just kind of, to assess the performance of the model. Depending on what that application is that we're after, so the performance measurement might be different, right? So for example, for a fraud case, right? Like let's say you're trying to discover credit card fraud, in that instance, I think the idea is you try to figure out what's the least amount of money that you can spend on investigating, because you have too many false positives, then you can investigate every single case. It's too much money. But at the same time, so you set some threshold for false positives, right? So
yeah, so for like power generation, for instance, like for some of these assets that we've talked about, can you explain how we strike that right balance of false positives versus events, right? Because on one hand, we don't want false positive for everything, right? There's one thing to be said for finding every little thing, but how do we start to find that right balance so that there's not too many alarms, but we're finding the right alarms?
Yes. So again, I think maybe the credit card example wasn't the most relevant here specific to this audience, but at the same time, like let's say like if you have this generator, there's certain modes, let's say, that are indicative of certain kind of maintenance event that needs to happen. Maybe it's an oil change, maybe it's some kind of a routine maintenance event. You might discover that, but you will set up certain tolerance for that specific event to be lower in the priority list, right? As opposed to something that might be new that the machine hasn't seen, that might strike. We can't tolerate any false positives.
Yeah.
Any instance that comes up across that specific cluster would have to be addressed. Does that make sense?
It does.
Okay.
It does. So I wanted to share a few of the best practices here. Typically when we're undergoing a machine learning project, we want to use at least 6 months to 2 years worth of historical data. That typically gives us the best results. We're using most of that data, that historical data, to actually train the model, and then about 15% to validate and 15% to test it. I think what's really interesting about our approach is that we're building these asset-centric models. Now I'm going to actually advance the screen real quick to kind of do a little bit deeper dive into why this is important. But essentially, we found three key groups of, I guess, things that we want to characterize. So in one case, we have scenarios where there's a lot of unknowns, right? Where, you've got a failure mode that occurs very rarely, it's hard to track, but when something fails, it is a high risk issue. We also have a scenario where, you might have a group of known failure modes, but they occur very sporadically. There's not a whole lot of leading indicators on when or how it might fail. The failure mode occurs, right? And then you have another scenario where, there's some well-known and well-documented failure modes that occur regularly. They're a little bit easier to predict. Now, with machine learning, we can actually, we apply machine learning differently to those problems. So for instance, with these unknowns, we use a clustering methodology to basically just identify what's new, right? we can't necessarily tell you if it's good or bad, but we can tell you that something in the asset has changed, right?
Right.
Now, another way that for scenario 2, we use an approach called normal behavior modeling, which is essentially, okay, let's look at all that historical data, all of the historical data from the normal operation of that asset. Let's build a really precise model around how we know that asset to behave well it's normally, and then calculate a risk threshold based off of standard deviations to that normal curve. So that's another way that we can actually
there's a technique which is really interesting. It's called T-squared hoteling, effectively. It's a really interesting technique they use anyway. But generally speaking, please go on, Gabe.
Yeah. And then like this last scenario, if it's a pattern that's well known, we can get really good at matching that behavior pattern and flagging an alert.
Yep.
So we're looking for these 3 scenarios, we're looking at different things. We're looking for new anomalies. We're looking for a threshold, standard deviation that exceeds the threshold based on that AI normal behavior model, or we're looking for a pattern that's matching really closely. The next thing you have to do, though, is you have to make it usable, right? We have to expose. We can't just say, hey, there's an alarm, go crazy. What we're trying to do with explainable AI is really try to unpack, okay, what is this anomaly? What does this behavior change mean, right? What is the context behind it?
Right.
So we try to surface as much of that through our UIs as possible so that the SMEs who are still in the loop, actually diagnosing and recommending, have as much information as possible to diagnose and actually inform the repair process.
Mm-hmm.
What I also get really excited about is with the continuous learning aspect of machine learning in general. The models that are developed are continuously being fed new data. They're being fed user inputs, and you just can't retrain statistics or rules-based models the way you can a machine learning model, right? The machine learning model is going to start to learn over time. It's going to find these behavior patterns. It's going to get better the longer it's deployed, and it's over the long haul, much less maintenance overhead actually goes into the upkeep of that model.
That is correct. Yep.
So I think another question that I get asked a lot when I'm with customers is really around, okay, data accessibility. What should I know around data accessibility? When we're working with customers, I know there's a lot of times just the biggest hurdle early on in the project is getting the data.
That's right.
Can you share some of your learnings and some of your thoughts around, okay, data accessibility?
Yeah. So the interesting thing about the data is sometimes you may not need the data to actually start a customer engagement. Other times that's critical. To give you an example, I guess a good example would be, let's say that you're working with a team on the customer side that has already has deployed certain AI solutions. They're just trying to pivot a little bit and go towards a different solution, right? So their organization is familiar with bringing on third parties, giving them API access fees to their their OSI Pi data, whatever the data lakes they have. So a lot of times, that data, the access to historians are there. And sometimes when you have a new client, for example, it's preferable to have the data to begin with, because a lot of times you still don't know, what you need to be looking at, whether you have the relevant data or not that might be, valuable for the predictive model that you build. So it just kind of depends, really. I hate to give these depends answers, but generally speaking, yeah, I mean, the more the customer is, I guess, down the journey with AI, the easier it is for us to work with them and access their data, and they know exactly where to point us. And I guess the less the earlier on they are, the more challenging it can be for us. But generally speaking, those things are workable.
Sure. So where are you most frequently accessing the data? Can you talk a little bit about these data lakes? Like what's industry standard?
Yeah.
What do you connect with? Like can you talk about kind of?
Sure. So basically, cloud solutions have become pretty pervasive. I mean, they're pretty common right now, especially in the commercial sector. So a lot of times you'd have the Google clouds of the world, whatever. They might have their own cloud solution as well, where they have their own historian, like an OSI Pi, which you can access. Sometimes it can be something that they just basically give us the port access, and we can basically pull data from there. Generally speaking, we actually get just regular CSVs. So a lot of times when we start an engagement, we just get a flat file that is, it's probably going to be, a lot of back and forth going on just to make sure that we understand what that CSV means. Sometimes you get multiple files, and then you have to figure out how do these tables relate to one another. But for training purposes, we can start with something as little as, or maybe, let's just say, not as super sophisticated, doesn't require like a database, just a regular CSV flat file. So.
Gotcha. Now, I know typically when we're connecting to an OSI Pi or Hadoop, but it's typically not a barrier to actually connect, to build the infrastructure to connect the data.
Yep.
The actual issue or the roadblocks that I hear about most are really on the IT side.
Oh, that's right. Yeah. So I can just comment. The technology, I'd probably say, is the easy part. The hard part is navigating the various IT policies that companies have implemented. And so again, that's part of the reason why it's easier to work with customers that are farther along their AI journey. They're already familiar with that process. They already know exactly how to create and navigate those internal policies with sharing data with, third-party vendors effectively.
Yeah.
So
I know security is another hot topic, and this is probably for a whole nother webinar.
Yeah.
But essentially, can you speak real quickly about the kind of the needs for security, for data security on cloud versus on-prem? Like what are the things that our customers need to know about regarding security?
I mean, we typically, when we have an engagement with a customer, I mean, obviously we do have some kind of a data sharing agreement, non-disclosure agreement, those, so we do have to follow the rules to make sure that we're not in violation of their security policies, right? So for example, if they have, it's less convenient for us, but generally sometimes you have a customer that basically does not have any cloud access or no internet access, sometimes you just have to, get on-prem and get that data, and then silo it into a flash card or something like that, and then work with that within your own infrastructure, and then go back and forth with that. I mean, when things are in the cloud, it makes things much easier, honestly.
Gotcha. So if we're going to turn this into some actionable recommendations, like I know what I hear a lot is really, okay, at the start of this AI project, make sure that you're already starting to think about the policies and the IT needs early on, right?
That's right.
Because it's going to accelerate the process down the road. So I think the other thing that we've heard is, get a champion from IT as part of this decision-making team to make sure to have their buy-in, and then test the network infrastructure for real-time streaming throughput. Now, I think the other thing that's somewhat unique about Spark Cognition is we don't own any customer data, right? We use it to build models, but at the end of the day, we're not.
That's right.
This, right?
That's right. So I think the customers own their data. We just use that to train the model, and then the technology, our IP is specifically on the technology that builds the models, right? So that's kind of how we marry those two things together. So their data, and then our technology applied to their data to produce a model. So now, generally speaking, then I guess the natural question would be, who owns the model in that case? Well, model is specific to that data. So it would be the customers. The technology is ours. Yeah.
Well, yeah. So the model that we build, though, we own the model, but we license that model to our customers.
Correct. Yeah. Because it runs on our technology.
Gotcha.
Yeah. Mm-hmm.
No, great questions. So I think moving on to this last four pillar is really around reproducibility. All right, so we've tackled a lot of the data questions already, but how do you scale? And I think that's what some of our customers are already starting to think about. Okay, we've done a proof of concept, we've done a pilot. how do we scale this in a way that's sustainable? And I'd like to provide some tips and some guidance on, okay, how do we actually, what's needed at a data level to support this scale? What helps that process? Mm-hmm. So can you talk a little bit about, how important is data infrastructure, the data acquisition infrastructure?
Oh, it's critical. It's a very simple answer, but the data infrastructure is one of the key aspects of making sure that you're getting the data in a certain format that you can reproduce. So basically, if you don't have the right data or not in the right format, you're creating potential roadblocks where it just gets in the way of being effective and efficient with building models.
And you could argue that a sensor reading is just sensor reading, but it's more nuanced than that, right?
Oh yes, yes.
There's standardization that's actually important at a data acquisition system. You don't want a bunch of variable data sets, right? You want a standardized.
Yeah, you want consistency. Yes. So sensors, the sensors have to be calibrated. There has to be policies around when those sensors need to be replaced. There has to be policies around even just tracking drift. A lot of times, accelerometers will under high vibration environments, sometimes those sensors will start to fail over time, right? So there has to be policies around making sure that we're getting good data output from that sensor.
Yeah.
So
what are the implications? Like, let's say the equipment is all disparate, which is probably a likely scenario, right? Different plants, different assets. The equipment is likely to be different. What are some of the implications of that, and how do you fix that, and how can our customers start to solve that problem?
Yeah, so you're right. Going from generator to generator or turbine to turbine, you might have certain features that are kind of unique to that specific one. But a lot of times, if you're working with, let's say, a gas turbine, a lot of times you're going to have certain features that are common across. By features, I mean data coming from the sensor. Yeah. So you may have certain sensors that are common across all of them, right? So how do you train? Well, training a model is the easy part, honestly. So it's usually it's the part that's I guess the challenging part is understanding what that data means. What does that sensor represent if it's unique and different, right? So it's just a matter of being able to understand on the customer side, like if they can have a good policies around, like, hey, when we basically expand the capabilities, let's say of a plant, we bring in an additional generator, it has to be consistent with the other generators, how they're all going to basically collect the data, right? It makes it easier for us to understand what various columns mean if the names are the same, right?
Sure.
So does that make sense?
Yeah, and so the point that I'm taking away is that the closer everything is, the more similarly everything is instrumented, the easier it is to rapidly deploy the models, because we're not having to deal with a bunch of different features.
Yes.
And it's going to ultimately result in speed for the customer, speed of delivery for the customer, and higher quality models for the customer. Now, I know kind of having the everything perfect is kind of a pie in the sky shot, right? The reality is that our customers are going to have different data acquisition systems. Yeah. But if you're looking at expanding, if you're looking at instrumenting your equipment, start to think about how do you standardize your measurements, how do you standardize your feature sets, how do you standardize how you actually collect the data, because that is what's going to drive scale long term, right?
That is correct.
So that's kind of the takeaway here. The best practices is, start thinking around standardization of not just the data acquisition system, but also the sensors. Make sure everything's calibrated. Make sure you're standardized around your IT and networking infrastructure. And this is going to directly affect the data quality that we talked about earlier, and it's going to directly impact the ability to scale.
I agree 100%.
So let's go ahead and put this in context with a customer story, right? It always helps to kind of show how customers use the data. Now, we worked with a power generation customer a little while ago who had just deployed 9 brand new combustion turbines. Now, they'd been collecting data for a little while, but because there wasn't any long operating history, there were very limited failures. Now, this is one of the use cases that we talked about earlier, where you're looking for unknown unknowns, and this is one area of machine learning that's really, really valuable and really useful. But essentially, this customer had a combustion turbine, one of these new deployments, fail early on, and so they were like, okay, well, we don't want this to happen again. Let's use this as a forcing function to investigate and evaluate how machine learning can not only help them find those unknowns and manage their risk, but then also help their SMEs start to understand the different behavior patterns that exist for those brand new assets. Now, there's an animation here on the screen, but if you've worked with the combustion turbine before, you know it's a very complicated piece of machinery, right? There's a lot of moving parts. It's a critical rotating piece of machinery. And the stage that was actually impacted was in the compression stage of this combustion turbine. So you can see here in the diagram that there's these blades that are held into place. So there's these blades that are held into place by a little retaining pin, and over time these as this wears, what we started to notice was that there were additional nonlinear correlations between a vibration measurement and a temperature measurement that weren't large enough to trigger any known alarms. Yeah. But it was a brand new pattern that we had never seen, that the SME had never seen before. Yeah, yeah. And so, by unpacking it a little bit more, they ended up taking this turbine down. But what had happened was that retaining key had failed, causing that blade to wiggle loose and start to rub up on the casing. Oh, wow. Now, had this behavior continued to happen, there could have been a catastrophic, or it would have expected to be a catastrophic failure for this particular blade and cause massive secondary damage downstream of that combustion turbine.
And I'm assuming they didn't have, I guess, there was no specific sensor that would have caught that, right? So it was really a combination of multiple things kind of working together. That just kind of happened. Is that kind of what happened here?
Exactly. It's a brand new correlation that a human had never programmed in to find that specific variable, right? Yeah. Yeah. But machine learning was able to say, hey, this is a new pattern. Let's surface this as an anomaly, and and our UI helps give a lot of additional diagnostic capabilities to the SME. Yeah. So they were able to look at, okay, can we rule out that this is a sensor issue? Do we have enough evidence to actually qualify that and make a recommendation to take the asset out of service? These are some of the explainable features of AI that are really valuable to help not just find those unknown patterns, but also help to explain and build that story around why an asset might be failing. Right?
Interesting.
Now we do this through a product called Spark Predict. Kind of a quick shameless plug here, but Spark Predict is a leading predictive maintenance product that is really geared around reducing those unexpected downtimes and costs. I can't tell you how many times I've heard from a customer that every time we get hit with an unexpected issue, it wrecks our O&M budget, right? Yeah. So if they can get more clarity around what to expect, we're helping them identify those known and unknown failure modes with enough lead time to actually take action and fix the problem. Through the explainable nature of AI, we're helping to accelerate the diagnostic and repair process as well by exposing, as many insights as we can that can help troubleshoot more effectively. And like we mentioned earlier, by streaming new data and by constantly getting feedback from the SMEs and new data, we can start to build an operating profile for this. We can get better at understanding the behavior of these assets over time. So it really speaks to the power of machine learning. Right. Now, Spark Predict is kind of built with 3 chunks. There's the model execution pipeline, which handles the ingestion of data and the cleansing of data, like you mentioned earlier.
Mm-hmm.
There's the model building piece that takes that data initially to build a high performance model of the asset. And then we extract insights of the failure modes or the normal behavior model and surface those through a UI for display. And all these three pieces are actually configurable. So what that means is that we can, deploy at an asset level, we can deploy in a system of systems, and we can deploy on a site level. So it's really expediting the process from starting with data and taking it all the way to a deployable model. We've been able to reduce that time by quite a lot.
Yeah, so interesting that the process in discovering and building models. How does it all start, right? Like how do we take advantage of deploying something that might produce a lot of value for organization? So we would encourage you to basically reach out to us. You have my contact details. You will also have the website, so you're able to basically point, put your information there. Possibly start talking to our salespeople. Gabe, do you have any other ideas? But effectively, we start with a flat file. We can talk about the use case. So that's how it all begins.
Yeah, no, absolutely. So what I think we'll do there is, we spent about 45 minutes on content, but let's go ahead and start taking some of these questions. I've seen some questions come in.
So I'm looking at a list of questions here.
Okay.
So the interesting thing is, and by the way, we're probably not going to go in. We don't have to go in order, do we?
No, we take them as they flow.
Yeah.
As many as possible.
Yeah. So basically, what is the typical ROI for your AI services? So again, I think that use case that you showed with a gas turbine.
Yeah.
I don't exactly remember precise numbers, but it was. I mean, the predominant cost was the downtime, right?
There's kind of two avenues here. There's one, the cost of repair for that massive failure, right? That the estimate that we got from the customers, the repair would have cost $500,000 to $1 million and would have taken that turbine out of service for about a month.
Wow.
Now I think the bigger piece is actually the opportunity cost, right? So that month out of service is based on about $40 per megawatt hour. Like it's about $13 million of service, right? So
lost revenue, right?
Exactly. So that starts to add up, and that's.
Yeah. That's pretty significant. So the next question is, so do we have a Spanish version for Latin America? We actually have a huge presence in Latin America. We have lots of partners that will work there. We have lots of projects. A lot of our we have some data scientists and sales expertise and business expertise dealing with Latin America. So yeah, absolutely. The answer to that question is a resounding yes. So and then also let's see. In your experience, is reliability and maintenance data stored in the same database as other relevant process data? Wow, that's a good question because no. The answer to that is typically no. A lot of times you will have multiple different databases and they're all collecting information at different frequencies. So it's the process of how do you reconcile the differences and then pre-process the data to feed into the model. But then the wonderful thing is we actually have worked with that. As I mentioned, we have Hermes. It's a tool, proprietary tool that we have developed that allows us to basically make these connectors that basically connect to the various sources of data and then kind of aggregate everything that we need, and so that can be ingested into a model.
Yeah, so let's go through here. Yeah, so kind of expand on it a little bit, but can you elaborate on how detailed the failure and maintenance logs need to be, and in what format?
So failure and maintenance logs are very important because they effectively, that's what we use to classify an operating mode, right? So for example, if a normal operating mode is let's say you have a gas turbine that is running on one type of fuel, right? It will have one normal operating mode. If you change the fuel, it might exhibit a different operating mode, right? Now, same thing with failure data in these maintenance logs. So depending on what kind of maintenance activity that you're performing, the pattern that your sensors might be producing might be very exclusive to that specific thing. So in a way, if we actually train the model to recognize a certain pattern for that specific maintenance event, that allows us to basically say, hey, we're getting pretty close to the risk profile of potentially exhibiting this, this specific maintenance event might be triggered. So that allows, and that's precisely the value of using machine learning like this, is you're able to actually not service your equipment based on time intervals or thresholds, but based on what the machine actually needs.
Yeah.
So
no, great answer. Okay, so reading through a couple more of these. So I think there's an open question around diving a little bit deeper into the actual detection of the failure for that turbine example. Okay, so why was a sensor placed there that enabled us to detect upcoming failure? Now, this is instrumented as part of the deployment. So it wasn't necessarily the placement of the sensor, but it was the unique correlation of two variables changing in different ways at the same time that actually enabled us to define that. So it was a vibration and temperature. So it was, I think, less involved when the actual placement of the sensor, but the two variables that changed at the same time.
That's right. So there was definitely, I would assume that there's probably not a sensor at each pin there, right? So what happened, I'm assuming, again, I'm not very familiar with that case, but it makes sense from a machine learning perspective that your model would be able to catch a certain correlation or certain pattern how various sensors interact with one another in a way that's anomalous. So that's precisely what has led to this discovery. I mean, that's what machine learning is all about, actually.
Yeah. So I think there's a little bit deeper dive on that. So what is the accuracy of predicting failure after 6 months? Now, I think there's different ways to actually categorize how do you predict a failure, right? So if you think about that slide of the 3 scenarios where, if we know what that failure looks like and we know what what it looks like before, we can use like a supervised approach to predict failure. But for the combustion turbine, it was actually a different operating mode. We detected a new behavior. We didn't necessarily say whether it was good or bad, but we detected a behavior state change, which is the way that an SME can interpret that, or can actually look at that and interpret the data available and actually make a judgment call on whether there's going to be a failure or not. So the point I'm trying to make here is that, the SME for unsupervised learning, the SME is still very, very involved in the process, right? There's a validation piece of, okay, we can give you a bunch of information, but because we haven't trained on this specific failure mode because we've never seen it before, the SME still has to do a little bit of legwork to actually qualify if this is going to be catastrophic or not.
Right. So I'm looking at a question here. So it says, I have data which consists of various attributes related to turbines, which can be exported based on the time period requirements. My main question is how to incorporate the time feature on the data. On calculating the day count pertaining of some fault, I noticed fault A is not limited to 2 months or 6 months. It varies. Fault B can also be 2 months or 6 months. So how do you distinguish the faults? That's a great question, by the way. And so yeah, a lot of times it's really not about time, really. That's not the driving feature that allows us to find things. What's important is capturing operating modes or various failure modes, right? So, and then understanding when your machine or your data transitions from one operating mode to another. So the closer, so let's say that, in examples of clusters, right? Let's say you have this multi-dimensional cluster space, and then you have certain clusters that are indicative of a certain kind of failure, and then you have multiple clusters that are indicative of your normal behavior. So really, sometimes what you can monitor over time is how quickly does that transition happen, right, into that failure cluster mode, right? So, and what sensors could be good lead indicators of that kind of the onset of that transition, right? So it depends. Some clusters you may get a warning that's like 2 or 3 days, which is not very helpful, or very, very short, right? And other times you may get a failure that certain modes they move gradually. So it allows the plant to operate, kind of plan for maintenance in a kind of a more intelligent way, because you can kind of, that specific failure mode isn't going to be imminent. So you can kind of plan your maintenance events around clustering certain, services.
Yeah. Okay, so another question come up. Is accuracy of prediction greater with different types of API interfaces, like Modbus, SNMP, et cetera?
Honestly, I do not know how to answer that question, because I'm not familiar with Modbus, SMP. I wish Lee, would you?
He's already. I think he's already up. So, okay, we'll move to another question.
Okay.
Here.
Okay.
All right. So another question around. We talked a lot about the machine learning piece, but I've got another question around what other AI technologies play into the vision for like a total plant solution. And this is a great question, because we focused on one piece of the puzzle, right? Making better predictions. But there's all sorts of workflows that happen after the fact as well, right? How do you look at, if you're going to actually drive scale and actually deploy a scalable solution to an entire plant, you have to start thinking outside the box, right?
Right.
So if you can solve the piece of making better predictions with a product like Spark Predict, the next step is, okay, how do you actually execute and accelerate the workflows around repair? So this is where we can use technologies like natural language processing, for instance, to pull in unstructured data from user manuals and repair logs, and serve that highly relevant information up to the right person who's actually performing the repairs. So we've kind of taken the predictive piece and accelerated all the way through to the repair.
Great answer. Let's see.
Probably have time for about one more here?
Yeah, I'm trying to figure out which question do I want to answer, because there's quite a few here.
All right, so, okay, when modeling the performance of an asset, do you use the manufacturer's data, the technical configuration, and do you end up with a plug-and-play modules when you manage to train your model on a number of turbine compressors from manufacturers?
Yeah, I feel like it's such a deep question. So basically, I'm gonna try to, so when you have multiple components and which is usually the case, you have multiple components, possibly multiple turbines, possible compressors, or whatever you're dealing with, right? So you do want to build models that are specific to that asset, because sometimes you may have, it could simply be that same compressor, but one compressor had an oil change done maybe 2 months ago, and this compressor just is relatively new, and we don't even maybe there's no data. So it might be transfer learning is not mature enough for us to actually start using that. So we typically build models per asset, and then we try to, sometimes we kind of all tie them all together at the higher level, right? When you have multiple models taking care of various assets, and then kind of all stitched together in a kind of a master model, if you will.
Yeah, exactly right. We're training the initial model based on the specific operating data from that turbine,
yep,
or from that asset, which is different than just getting a bunch of manufacturing data. It's going to depend on how that asset's deployed, where it's deployed, what weather events. I remember with the Arctic storm that just came through, right? how could anyone have anticipated how those models react?
Yeah,
right?
that's
So
right.
all these unique features are really important that we capture them in the historical data for that particular asset. So I think there are a couple questions that we didn't get to that we'll try to follow up by email, but we are at the top of the hour again, and we just want to thank everyone for joining. Once this is, we will send out this recording here in about a week or so, so stay tuned for that. In the meantime, feel free to reach out if you guys have any questions. But thank you all for attending, and we hope you guys have a great rest of the day.
Thank you.